start recording because I think this is likely as many folks as we're going to have for today. So welcome back to our last class of the semester. I should be caught up on grades, so I processed them again just I think yesterday. Homework 5 is the only thing that's outstanding. If you want, you can see where your grade is sitting right now if you log into the homework portal on the entry page where all your assignment access points are. You can see your current point totals, not including homework 5 and not including any bonus points. So as a reminder, if at least 30 of you submit a university course evaluation by Saturday night, I'll give the whole class one point of extra credit. Right now we're at 19 and we need 30. And I had sent out a Qualtrics survey on Tuesday that if you complete it, you get a point of extra credit for doing so. It helps me get more detailed feedback about your experience that I can use for hopefully planning better classes in the future. So those are the other things that are on tap. Am I forgetting anything logistically? Yes?
Just one. I mentioned it before you started the recording, so I guess to have it on the recording that I am going to be available tomorrow for office hours and also on Tuesday, but I will not be available next week Friday because everything's due before then.
Yes, thank you. And same. I have office hours Monday at from 12 to 1:30, Tuesday from 12:30 to 2:30, I think, or 2, the 2, 2:30, and then Wednesday from 3 to 4:30. So if you need any help with anything and want to get the stuff wrapped up, these are your chances. After that, then it becomes moot. All right, then let me get the screen share started so we can talk about caveats and next steps. Putting this all together here. So, and I like to see your faces. If you want to have your cameras on, I would like to see that. If you're like, there's dirty laundry in the background and I don't want you to see what my house looks like, that's fine too. Fair enough. All right, so can everybody see the slides? Hear me and see me okay? We're good? Okay, excellent. And I've still got, let me get the chat window back open so I can make sure I can watch that as well. Catch those. Okay, cool. All right, so away we go. So this was my opening slide this semester. 2 reasons why you are here. And the first reason may still be quite valid, because I have to be. This class is required by a lot of programs in the College of Education. It is a baseline course for a lot of programs across the university. And that's fine. If you're like, I have to be here and I was here and now I'm done, great. I hope that you have been convinced at least a little more in that case of the utility of quantitative methods and maybe feel a little more comfortable reading research that use quantitative methods. What I hope is to have pleasantly surprised you that you can do this and that maybe it isn't as fearful or difficult as you would have expected. The material that we've covered this semester, I feel, is a foundation of basically all of quantitative methods. The question is what else you would need to sort of add to it so that it would work for different kinds of data problems. So what I wanted to do today is just review sort of where we've been across the semester, sort of big picture ideas and vocabulary, and then start to think about what are the requirements that the data should have for these models to be believable. But then what do we do if they're not? There's a lot of regression textbooks that present assumptions, and you're told these things have to be true. There's three big ones. But you're not really told what to do instead if they're not. And I've always found that kind of dissatisfying. So I wanted to put this at the end as a bridge to the future for you. So the steps that we have covered in terms of how you would approach a statistical analysis using a continuous or continue-ish outcome. First things first, understand the research questions and the types of variables to be used in answering them. So I've done a whole lot of statistical consulting work in my life, and that's always my first question. It's like, tell me about the data and tell me what you want to know. And then based on those answers, I'm sort of cataloging what needs to happen. But which variables are needed will dictate how they fit into the model. And then the question is, are they predictors or outcomes? And it is possible in more complex models for a predictor to be both at the same time. But in these models, that's not the case. So you kind of have to pick a lane. Are you thinking of this variable as a reason why something happens? That would be a predictor. Synonyms include regressor or independent variable, particularly if that predictor were randomly assigned and manipulated. And then what happens that you want to predict is the outcome, or criterion, or dependent variable as it is known. In terms of kinds of variables, there's really two major distinctions to keep track of. One is quantitative, in which it's a numeric variable that truly the numbers mean numbers. It may have boundaries, it may not be continuous, but it is something where you can interpret a 1 unit change and think about what a unit is. So a year, a pound, an inch, a dollar, that kind of thing. Categories, then, is the other kind of variable in which the numbers might be used to store which category a given row belongs to, but the numbers are not numbers, they're just labels. And in that case, you need to know how many categories you have in order to figure out how they differ from each other with respect to their outcomes. And I have a note here, the general linear models we've covered this semester are for quantitative outcomes only. There are other models if you have different kinds of outcomes, as we'll talk about later in the show. So we have step 1, and then we go to step 3. That's on purpose. Step 3 is how to determine how the predictor variables get put into your model. So if it's a quantitative predictor, you need to think about what 0 means. Is 0 part of the natural range of this variable, or does it not include 0? If it doesn't include 0 as part of its natural range, then we would want to center it by subtracting a constant so that 0 becomes a meaningful reference point. And this is useful to create a meaningful intercept as the expected outcome when your predictors are 0 at a minimum. But as we just saw in the last unit and in homework 5, the main effects of predictors become conditional on the 0 values of any variable that they interact with. So that's another reason why you want to make sure that 0 means something within the scale of your variable, and to basically rescale it if that is not the case. The good news, though, is that what constant you pick doesn't really matter. Like, you can have a scale from like 1 to 5, for instance, that you're thinking of as numeric, which a lot of people would, and you could pick 4 to center around as the midpoint, or if most of the sample answered like 3 instead, or you could pick 3 as the midpoint, or you could pick 4 if that's a more common answer. Like 3 or 4 isn't going to change how effective the model is. It's not going to change your R-square, your predicted values, or any of that. The centering point changes the intercept and the main effect slopes of any variable that that variable interacts with. For quantitative variables, then, we want to think about how they are related to the outcome. Linear is the default. So we would have a linear slope as sort of a starting point, but there's other choices. And so in example 3, I think we had a quadratic model with age. So we had a parabola, like upside down shape with that. Exponential creates a line that sort of like trails off a little bit. So if something like stops mattering, you can fit basically by log transforming the predictor, you can fit a curve that looks like this. We talked about piecewise or spline models where you break the variable into sections, and then you can fit separate slopes in each section to answer questions about, relative to these like knot points or break points, how the variable functions. But ultimately, this is an empirical question. You can round your quantitative variables into convenient integers and plot their means and just look, like, does it look like it's going up linearly? Does it look like it's leveling off? Does it look like it goes up and then comes back down? So I think theory, in terms of what you theoretically expect these relationships to look like, plays a role, but then also ultimately your data can help you decide. So these are the choices that I would point towards in terms of flavors of nonlinear that are readily put into general linear models. If we have a categorical predictor, though, then we can't put it in as is. So we have to essentially carve it up into separate binary contrasts so that we can differentiate all possible outcomes across the categories. So I showed you 2 different types of coding. There are many, many more, but these are the ones that I personally find most useful. Indicator coding is like the universal default of the world. When people say, I put a categorical predictor in the model, this is usually what they mean. And I taught you how to build these new predictors and put them in the model sort of manually. I will point out that that process can be shortened in R by declaring a categorical predictor as a factor variable. So that can happen in a data set, or it can happen in an analysis. So for instance, if I have group as a predictor, I can say as dot factor and then put group in, and it will essentially do this table for me. It will designate the lowest category numerically, and I think either that or alphabetically, as the reference, and then it will build additional binary contrast to differentiate each other category from that reference. So this is like the default way of people approaching predictors. This is useful for nominal variables in which there's no natural order. So you might just pick whichever is most common as the reference and then talk about each one relative to that. Sequential coding is an alternative, and I've highlighted in blue here how it differs. The ones being filled in here make it so that it doesn't reset all the way back to the reference group. So this essentially creates steps between each ordinal category. So this would make much more sense for variables like strongly disagree to neutral to agree to strongly agree, those kinds of things. Because then you could see what is the change in the outcome from moving up each answer choice to the next highest level. And I will also note that there's a different kind of coding scheme that sometimes gets used called effect coding, in which rather than zeros or ones, it's minus ones and ones. And that coding scheme makes it so that 0 refers to the average, not any specific category. And I've always found that weird, and so I don't tend to use it. But that's another one that you might come across. Okay, questions so far or comments? Is this sounding reasonably familiar? At least the words, right? These are the big picture things that I want to take with you.
It's just one, just maybe a slightly different way to look at the sequential coding,
Yeah.
the way that you have it labeled at the top. It's like A or greater than A. You have less than B or greater than B, less than C or greater than C, because how you're dividing it up like that. And then you can do your subtractions to get, your A, your B, your C, and your D, so forth.
Yeah, I like that way of describing it, and that also maps onto the idea of a cumulative link function that is used in advanced models for categorical outcomes. So you'll see this kind of pattern again if you're predicting categories as outcomes rather than predictors. But yeah, that's a good way to think about it. Step 4, figure out what else you want to know that's not given in your output. So we've talked about, for instance, the reference group we get a predicted outcome for. And we get differences relative to the other groups, but we don't get what the predicted outcomes are for those other groups by default. We have to ask for them. And I showed you sort of a manual way to do it using lincom in Stata or margins in Stata, and in R it would be glht, but there's other ways you can do it, especially if you have factor variables. That's a very short piece of code to get all the possible means. But the point is that the model is only going to give you directly some of the things you care about, and you have to think about what else do I want to know and how do I build a linear combination to get that. So for instance, you might need to test new slopes. So within this right here, let's go over here to the indicator coding. I get the difference relative to A for each of my other categories. But the model's not going to directly tell me about B versus C or C versus D. Those may be additional comparisons I want to report, but to do that, I have to find the difference between those slopes. So that's an example of a new single slope that you might need to request for other predictor mean differences. Another example of when you might do this is if you have predictors that are on the same scale and you want to see which one is more important. So I can't remember if it's this class or a different one, but I had number of papers and number of posters. No, it's a different class now. I remember that because the outcome is binary. I had an example in a different class where I had the number of graduate students predicting whether or not they're going to get a job from their number of papers and their number of posters. And so one more paper or one more poster is the unit. So I asked a question, which has a stronger effect on the likelihood of getting a job. And so that requires a comparison of the slopes for these two variables to see if one more has a bigger impact on papers versus posters. Another example of this is simple slopes or conditional slopes for non-reference groups and interaction terms. So if I want the grip strength slope at age 85, that's given to me in the model directly if age is centered at 85. If I want it at 90, I have to ask for that. And so we've seen many examples lately of doing those kinds of comparisons as well. Another thing that you may need to ask for are tests of slopes lumped together. So for instance, if you have a test of the model, that f-test that shows up first in the output is lumping together all fixed slopes that you have in the model for one joint hypothesis test that basically says, hey, what if these were all zero? And you get a test statistic for describing essentially how likely that would be relative to the null hypothesis as the baseline. If you want to talk about the change in R square from adding a set of new predictors, you would ask for another f-test of these lumped together. If you want to talk about the overall effect of group, for instance, when you have more than one group, like you want to lump these things back together again so that you can talk about does group matter, that would be another f-test. And that has a special name in analysis of variance language of omnibus, overall. So you'll see that phrase used as well. Step 5, effect sizes. So we know that all things being equal, slopes that are found in bigger samples are more likely to be significant, meaning outside the boundary of expected based on the standard error for expected fluctuation of that slope across samples. But that doesn't mean the slope is practically significant, like it matters. If you have a large enough sample, you can have a teeny tiny slope be significant, but it doesn't really contribute much to the prediction and it doesn't have a strong relationship. So besides reporting the direction of the slope, the significance of the slope, we would want to report some measure of effect size that quantifies in a more absolute sense, like how strong this relationship is. The question is what kind of effect size? So what is always okay to do is for each slope in your model to compute a partial R or to compute a Cohen's d. And those provide the size, effect size for that slope relative to just the residual. So these ones are the like, of what's left, how much did this get kind of idea, where you're factoring out all the other slopes that are in the model. And so Cohen's d is in a partial like style in the same way. And this is useful for predicting power. It's not useful in terms of talking about R square. And this is the one that can be artificially inflated by adding predictors that further explain variance. So if you have less residual variance, your effect is going to look stronger, which seems sort of unfair. What can be okay, but not always, is semi-partial R squared. Now, I like this one for the simplicity of its interpretation. It's the amount of the model R squared that predictor was responsible for. Seems pretty straightforward. However, you get into problems in terms of trying to combine slopes that express one common idea. So for instance, if I have those group-specific contrasts, the binary coding system, I can't compute a semi-partial R square for each of them because their total is going to sum to more than what it should be because they have interdependency that has to be taken into account. The same is true in terms of the lack of utility of this for simple slopes because that simple slope depends on where your moderators are. So you would have a different effect size based on your centering strategy, which seems a little like, I don't like it when that happens. So these ones are a little trickier in terms of how you would go about combining terms, but if you're in a main effects model where everything is sort of working separately, then semi-partial R square tells you how much of the R square for the model that slope got, and that seems pretty useful to me. All right. Write it up and turn it in. That's step 6. One of my favorite expressions. The models that you're going to report are likely only a subset of what you used. The question then becomes, how do you do a complete and transparent reporting of your analysis and your process and your conclusions, yet not overwhelm your reader by telling them about every rabbit hole you went down or every permutation that you explored to see that something was working the way you thought? This is an art more than a science. But the key ideas here, that things you definitely need to report, your modeling approach. So you would say, I used general linear models, or I used multiple regression, I used analysis of variance, like give the noun that goes with the strategy. Report your software and the version. So it's not enough to say that you used R. You would need to say, I used the LM function in R version this, because things are not always backwards compatible across software packages. And there's been things where like at one point I got these results, but then the software defaults changed and I got different results later on. So the version number actually does matter along with this. You would want to describe your process of creating predictor variables, so your centering strategies, who the reference group is with respect to any categorical predictors, and equations can be useful. I would highly encourage you to use the equation editor to do this rather than just straight font, because it makes everything look nicer, and there's certain kinds of symbols that are only possible in the equation editors. If you know LaTeX, you can actually type LaTeX commands in the equation editor, and the same thing works in rendering equations in Icon, by the way, too. What happened then is part of the story, and you would want to do basically two languages of communication. There's one that I call stat ease, and that's the one where it's like f comma this equals this, p this, r squared this, like you're giving the results numerically, but then you also have to break it down for your reader, because no reader is going to highlight what your f was as the thing they want to remember about your paper. It's always the model was significant, f blah 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 blah, then indicating that, and then you give the conclusion more verbally. So, question, Michael? Comment?
When reporting all these estimates, etc., do you find it more common to have a table that you say reference table for this information, or do you see it more within the body of the paragraph itself, or does it really just depend on the writer and publisher?
Great question. I think it depends on the intent of the information. So I'll give you like two examples. If you're running a series of multiple regression models, I think it's fine to report the test of the model in the text, because you're not going to be comparing like what the F is now relative to what it's going to be in a subsequent model. Like you're saying, this is what happened, this is what happened. If your intent is to compare, then putting them in a table. So for instance, in running factor analyses, right? Here's the fit of my one factor model. Here's the fit of my two factor model, where you really do want to look and see how each of the values changed. That's much more effective in a table format than it is in separate places in the text. So I think anytime you want your reader to explicitly compare things, then put them all in a table. If each thing can kind of stand alone, then I think the text is fine for that. That's my hot take, at least. All right, so stat part version and then regular interpretation. And the results sections that I have in the homework assignment and the class examples try to illustrate how to do this, but they're missing a really critical part, and that is guiding the reader as to why they should care. Like you have to provide a working context that the reader can take with them. So if you start the end of your introduction of a paper before your method section saying, these are my objectives, or these are my questions, or these are my hypotheses, then your results section should be organized that way. Like, here's the analysis that answers question 1. And then, the indicating that as hypothesized, this predicted this other thing. So then you're tying it back to, why are you telling me about this? Oh, it's because I'm now answering question 1. So literally subheadings or just starting the paragraph with a link back to that then gives them the clue they need to carry the thread through. And also, nowadays, most journals are electronic. They're not even necessarily printed at any point. And so page limitations are less of a thing. And a lot of journals will allow you to submit supplemental material. So if you're on the fence about how much to include in terms of details, you want to be transparent and thorough, but you don't want to be overwhelming. Maybe stick to just the most important things in the paper, but build yourself a supplement that reports additional analyses that support your conclusions, or show that you did your checking to make sure that everything is, that these choices didn't affect the outcome too much, those kinds of things. And I would also encourage you to provide syntax, especially if you're doing models that are unfamiliar to your field, because people will cite your paper as like, I followed this person's approach. And I've had pretty good luck in getting my stuff cited, because almost all my papers have a supplement with example code across programs, example output, and resources that people can use to do things. So never underestimate the importance of these kinds of additional pieces that can help set your work apart from those of other people. All right, so what we covered this semester, general linear models are for predicting one conditionally normal outcome. So this is a new term that we're going to talk about today, what this idea means. We have quantitative predictors or categorical predictors, and then here are the more specific names that people would use for each of these situations. They are all united in the sense that what we believe to be true about the outcome is the same. These separate names only refer to differences among the predictors, and once you move out of the GLM, naming things differently as a function of what predictors are included doesn't happen. Like, we stop doing that immediately. So this is sort of overkill in my mind as in terms of the number of vocabulary words that are truly necessary to talk about this. So the missing step 2 then. The GLM requires several things to be plausible. And there are tests for some things, but there are not for all of them. These are generally called model assumptions. So there are 2 consequences of getting this wrong. Essentially, when what you need to believe about your data isn't actually true, or the data don't follow that. On the fixed effect estimates, you'll end up with the wrong depiction of how variables relate to each other. And in the section of our textbook that covers this, it's labeled as a primary type of misspecification. Or your consequences could include incorrect standard errors. So why does that matter? If we walk through the table, first column is an estimate, right? Second column is its standard error to describe its expected inconsistency across samples. The standard error is how far off on average a given slope is from the population slope. Estimate divided by standard error gives me t. Then the next column over is usually p. There we go. Got my alphabet hands in place here today. So if I get the wrong standard error, let's say it's too small, because that's often what's going to happen, then t is too big and p is too small. So it like trickles across the page essentially. So if you screw up your slopes, then you're incorrect in how you're describing how variables relate to each other. If you screw up your standard errors, you're incorrect in describing how much confidence you have in the precision of that relationship. Some problems can be fixed by changing these sorts of models, and some of them require ejecting to a different kind of model or approach entirely. So I want to talk about what is actually assumed to use general linear models, and then what you can do about it if those things are not true. So questions or comments before we sort of change gears into this? Moving along. First one, is linearity an assumption? No. I can't tell you how many textbooks and tutorials have said that it is, and it's not. In general, the form of your model, like whether you say a relationship between 2 variables is linear or nonlinear, the assumption is that you got that right. Whatever you say the model form is now the assumption. So we've seen models that have nonlinear relationships. For instance, age and age squared creates a slope that looks like an upside down U, a parabola. That's still a linear model. The reason that it is this distinction right here. We have nonlinear in the variables is what is allowed in the GLM. That means we are adding predictors that bend the slope, but the way the predictors are being entered into the model is still a linear form. It's still slope times variable plus slope times variable plus slope times variable. That's a linear model. The alternative is something called nonlinear in the parameters, in which the form of the model doesn't work that way. So here's an example that I'm familiar with. This isn't a truly exponential model where I have the slope and then we have an e multiplying it with this stuff up in the exponent. So this is like logs and exponents. That's where we violate that linear form. So this is not a standard general linear model. It would have to be estimated a different way, and there would be different considerations in fitting it. Having something like age and age squared is still technically a linear model in the way that it's formed, even though it makes nonlinear slopes. And as I said, the big picture is that whatever form you say a slope has, whether it's straight or bendy, the assumption is that you're right. So you can add things to your model to see if you're right. So for instance, in example 4b, that was the old people cognition data set being introduced, I first examined quadratic slopes for age and for grip strength to see if they needed some bendiness to their relationship. The data said no, so I left them out. So you can add extra slopes that create nonlinearity and see if they're needed. For instance, you can start with a linear slope and then add in a log transformed version of that same predictor and give it a linear slope. And then that adds, like, that explicitly isolates like the nonlinear aspect of it. So that would be my general strategy, is to try other things, see if they're needed. That's really the only way you can tell You can ask for plots of things, but plots are very difficult to actually see problems in. Only if it's egregious would a visual of residuals actually tell you what's going on. So how about normality? That's another one that folks throw around. And of the predictors, no. We never ever have any kind of distributional assumptions about predictors. Otherwise, we couldn't have categorical predictors because they're not normal, clearly. Of the original outcome, also no. So there is no requirement that your outcome be normally distributed. That's not what it is. What we are assuming is normally distributed is E, the residual, the part of the outcome that is left over, the part of the outcome that is conditional after being predicted by the model predictors and their fixed slopes. So we say E is normal. And the thing is, you can't tell if E is normal until you have a model that creates an E. So a lot of textbooks will show pictures of histograms of outcomes and say, this isn't normal and we need to transform it, or we need to clean it, we need to fix it somehow. But that is misguided because it's not the original outcome that we're worried about, it's the E. So you will see in some textbooks standalone chapters on things like data cleaning or data transformations, and they're literally looking at univariate descriptive statistics and deciding to mess with their variables on that basis. That is wrong. We don't know out of the context of a model what is actually needed. And there is no requirement that outcomes or predictors be normally distributed, only the residuals that are left over. Another one is a mouthful. So constant variance is the way that I describe this because those are two easily pronounceable words. If you read about this assumption in a textbook, they will call this the assumption of homoscedasticity. And do you know what the opposite of homoscedasticity is? Heteroscedasticity. Add another syllable to it. So, or homogeneity of variance. And I stole some pictures from the internet that I thought did a good job of explaining what this means. So here we have X on this axis and we have Y on this axis, and the blue line would be a regression line that describes how X predicts Y. So we have like a middle point on the line, which is where we expect people to be. Said differently, the mean of the E residuals is always 0 because the mean is given by the rest of the model. The fixed slopes put us somewhere along this blue line. We're assuming that the scatter of residuals around that line has the same width no matter where you are on the line. So the distribution of the little residuals around here of the E's has the same standard deviation at the upper part of X as it does at the lower part. That's what this means. As an alternative, you could see a shape like this, and I like this picture for its simplicity as well. So good is because the dots are evenly spread out along the line, meaning the quality of prediction doesn't depend on where you are, right? Like you can be just as wrong up here as down here. And then this one is labeled not good because it is more wrong the further you get on X. So just having one variance in the model would not capture this pattern because that variance is probably like an average variance, and it would apply maybe to the middle part, but it would be too big for the values down here, and it would be too small for the values up here. And again, residual variance is the numerator of standard errors. So if you have the wrong variance estimate for that particular standard error, then that standard error will be potentially too big or too little, and it's going to mess up your p-values and your inferences. So when this would happen, for instance, is in variables with boundaries. This is a very common pattern in count outcomes because you can't have a count below 0. And it is easier to be right, like if you're hitting like against the wall, right? You don't have room to be wrong if you're predicting a count of 1. Oh, come back. There we go. I hit the mouse. I got too excited with my fan shapes here. I got a lot of room to be wrong out here, right? So if you look at this pattern and it's like, well, how do I fix it? Ugh. There's nothing really you can do about it. See here. Yes. So I want to point you towards like where you would go instead. Here's some more examples of when you would have that kind of fan pattern, predicting something like proportion correct. So that's a numeric variable, or number correct, it doesn't really matter, but they have boundaries, right? You can get everything wrong or everything right, and those are the boundaries. So you would expect the variance of the residuals to shrink as you get closer to those endpoints and to be biggest in the middle where there's the most room to be wrong. But it would be non-constant is the point I'm trying to make. And then count outcomes are going to have less variance towards 0 and more variance outside of that. So here's an example of the latter. This is from the generalized linear modeling class that I created here. This is example 3. Now this is a great example of an outcome that is definitely not normal, right? We can agree on this. Is this outcome positively skewed or negatively skewed? Yep, positive. It's where the tail goes. So this is an example. I'll tell you a very brief story where this came from. This outcome is the number of mean things said during a psychology experiment where they deliberately got people irritated. And so they had 3 different conditions in terms of how they told them to deal with their irritation, and this was the outcome. And the reason that I have these data as one of my examples and as one of my papers is because I had a student who collected these data come to my office hours and say, what kind of data transformation should I do to make this more normal? Like, no. Like, you could log transform it or take the square root to move like these extreme values sort of closer in, like you could kind of reel in the tail. But there's no data transformation on Earth that's going to take this pile of people who said 0, 45% of the sample, and somehow like spread them out on the other side. Like, this is not fixable by a data transformation. But what it is fixable for is a different kind of model that understands that the number of mean things said has to stay at 0 or higher, and that it expects the variance to increase as you move up the predicted outcome. So this is decidedly not normal. It doesn't need to be, though, if we pick a different kind of model potentially for it. So what do we do about it? In practice, normality is not the problem. It's the constant variance part. And the reason those two are linked together is because in the normal distribution, it's characterized by 2 things. They're called moments or parameters, the mean and the variance. And while we can say the mean can differ as a function of our predictors, like we get a different mean for each like profile combination of predictor values you have, the normal distribution has one variance to it. So that means it has to cover everything. You can't have like a variance for this kind and a variance for that kind. It's one number. So the normal distribution sort of locks you into this, but then you have to figure out how to get around it. So for outcomes that are sufficiently continuous, meaning that they're not counts, they're not categories, there's something that could be normal, it's just not, changing the way the standard errors are computed is an option for you. So this is something that you will see labeled as a sandwich estimator in the statistical literature. It is always explained that way. This is what it says. I've never once understood this in my life, and I don't think I'm going to. But it's some magical thing that essentially uses what the e's actually looked like in the model to figure out what the variance would be like at that point. So it's an empirical way to adjust your standard errors based on the patterns that are actually in your data. So that's one thing I'll show you. It's just one little option in terms of changing what the command is for the software to get this. Different packages, though, do this differently with different options. And so I wouldn't be able to get you the same answer key across 3 different packages if I'd used this. There's also something that you should be aware of based on resampling techniques. So jackknifing is an older one where essentially they would take one person out of the model, re-estimate it, put them back in, take someone else out, re-estimate it, and then that gives you essentially like what a distribution of samples would look like, even if you're just approximating it from your one sample that you have. And then you can get an empirical standard error as what the standard deviation is across those repeated samples. And bootstrapping is what people do more often nowadays. That is sampling with replacement to accomplish the same end. So you will see these approaches used to address situations of different variances as well as terms that don't have a handy-dandy standard error formula. Like if you've invented a new statistic and you don't know how to get the standard error, this is a way to get it from the data directly. So let me give you a couple examples here. So this is the data set that we just finished looking at, of the old people predicting cognition. And this is a plot of the residuals from a model that is missing one of the interaction terms. So this isn't great. You can see that we have this heterogeneity pattern where it's more wrong the further up X you get. This is, if the data were perfectly normal, you would see all the dots falling on this line. And you're seeing sort of a ceiling effect here because there's an upper boundary to what the values could be in this scale. So in SAS, I asked for robust standard errors, the sandwich kind. So I want to contrast this column right here, which is the standard version of getting standard errors just from their handy dandy formula, versus this one, which is estimating them from the data. So in this case, I know what the right answer is because I made these data. And this model is missing one term, the interactions with sex and dementia. What is it called? Yeah, I think actually it's missing both of those. It's missing the interactions with the dementia and sex. So in this case, we have basically the same results for the ones that don't involve the missing interactions, but the ones that do are quite different. So like this dementia NC effect has a much smaller standard error empirically than what the model is assuming. So in this case, we would have a stronger test statistic after we corrected for heterogeneity than before. It could work the other way as well. So here's the last model in example 4A. This was the previous data set predicting income in tens and thousands of dollars. This is not good, right? This is definitely a fan shape of not good residuals. We are more wrong in predicting income the higher we go, which again makes sense because you can't go below 0. So this is a boundary consequence. When anytime you have variables with boundaries, you're going to see this pattern. And this is, I mean, this doesn't look too non-normal, but I'm worried about the spread of the variance here. So I fit a model in Stata using robust standard errors. The command to do this right here is just this little thing. VCE is the command to get different standard errors through some kind of empirical means. There's various options within that. And HC3 is the one that I picked for this. So here's what we get originally. This was an example 4A. Here's what we get after correcting for heterogeneity. Now these are quite different, not just the standard errors, but the conclusions that we would draw. So it looked like low versus upper in terms of working class was significant over here. It is not significant over here. So p-value of 0.008 versus 0.085. And the standard error over here was 2 something, over here it's 4 something. So we're assuming that there's equal leftover variance no matter which group you're in. And this is suggesting that that's not plausible because it's moving the standard error around based on what actually happened in the data. And the same, like this is non-significant, this one was non-significant, and now it is significant. So it can go either way in terms of how this can affect your output. Because if you think about it, if you have an average residual variance, it's going to be too big in some spots and it's going to be too small in others. So it could go either way in terms of how this changes it. And down here is an example of using bootstrapping instead. And it comes up with different numbers, but there's sort of the same pattern in terms of which ones are changing to be relatively larger or smaller. And I found a nice R example here that I have a link to as well. Then problematic people is another thing that we'll have to worry about. I want to give you just a little bit of vocabulary. So the term, if you have an outlier with respect to y, like this person up here, is distance. It's a measure of distance as to how extreme they are on the outcome. Leverage is what it's called if they're extreme on x, so this person over here, and the bad guy is up here. This is known as influence. So if this C dot were in the model, the slope is being brought up to it, like it has more say in where the slope goes because it's a high leverage point where it's affecting the whole cloud. If C were not here, the slope should be 0. So the dotted line slope is what would actually be the case if there's no relationship shown as a function of the scatter plot, but then C is distorting it, so we get this positive relationship here. And you can ask for values as follow-up analyses to worry about this. Cook's distance is how much the predicted outcomes would change if you kick that person out. And another measure is DF beta, which is how much the slopes would change if you kick that person out. So the software will do this for you, essentially like kick out one person at a time and give you all the statistics. So then there are, basically you would look for relatively high values as potential indicators of problems. The question then is what to do about it. So I can see both arguments. From a fairness perspective, I wouldn't want any one person in my sample to have undue influence on where the slope goes. Like that doesn't seem fair to let C like have more of a say. But on the other hand, if C is a representative member of the population that I want to draw conclusions to, why would I kick them out? So you will see people do outlier analyses where they kick out cases. That always makes me really uncomfortable because at the end of the day, it's subjective. So I'll give you an example from my own work. In my dissertation data that I collected real data on older adults, there were 3 cases that were really extreme on one of my measures, such that when they were in the data set, it was significantly related to my outcome, and when they weren't, it wasn't. And I was like, okay, like, what lane do I pick here? So what I ended up doing is reporting the results without them, and then putting a footnote in that said that I did that. Like I looked at the conclusions, and these 3 people had a big impact, and that made me, feel squishy, so I didn't leave them in. So I tried to be transparent about it, but like those 3 people were very discrepant from all the others. There was no intermediate values, but in most cases, data, there's going to be intermediate. So if we go, pun intended, this is our class, right? If we go back to this picture, like who do you kick out? Here's somebody who said 24 mean things. They're the highest. 19? Is that still too high? Like where would you stop? That's the question, and it's subjective. And so I tend not to kick people out if at all possible. And then there's when to eject. So let me pause here for comments or questions. Michael, do you want to add anything?
Well, the one thing I was going to bring up is that, especially in R, maybe in Stata, different packages have the same functions, and so depending on your analysis, you may want to also mention which specific package you are using within R, because somebody might get a slightly different result just because of some programming items. And as far as the ejections or not, I would also think about sample sizes. For example, if you have like maybe 3 or 4 that are outliers out of 3,000, maybe that's okay to eject them. But if you have 3 or 4 and your sample size is only like 50 to 100, I would be more leery about doing that. That might be a sign there's a lot more people in the population that they're actually representing, and you don't want to get rid of that portion.
Yeah, that's a very important point. Like the proportion of your sample that you would be deleting has to be considered in addition to just how discrepant they are, as indicated by these values. So these are the kinds of things you would report to justify your decision that you kick this person out. So when is this not going to work? That's the end section here. There's only 4 slides left, guys. Can we hang in there? Just 4. I know, it's almost over. I can always see when the end is coming on my version of this. It's 21 and 25 here. So when to eject. I want to be transparent that what I hope you've learned this semester is not enough to do most modern quantitative analyses. Like this is the starting point. And it will lend itself to certain data situations, but they're not very realistic. So I want to point you towards the building blocks you would need to add to this set of content to make it work for more complex data sets and sampling designs. But everything that you've learned is still relevant. Like this is the jumping off point. It's the bottom of the pyramid. And then you're sort of stacking things on top of it that address these additional layers of complexity. So there are some kinds of outcomes that the idea that the residuals are normal is never, ever going to happen. So that's where you would move to a different family of regression models known as generalized. And ized means some kind of not normal outcome, some other kind. General models are actually a specific subset of generalized. So general is not the most general. It's actually just this tiny little one, and generalized is bigger, but then there's stuff over that too. Yeah. So these models swap out the distribution that the residuals are assumed to follow. So, and they pick one that is a better match for what the values could possibly be. So for instance, if I predict a binary outcome, ones and zeros, what's left of that is never going to be normally distributed. It can't. And it's never going to have constant variance because you have these boundaries. So there's a distribution called Bernoulli, which is some dude's name, that was developed in like, I don't know, the 1500s or something. And it describes binary data. And that Bernoulli distribution does not have a variance to it. Because once you know the mean, you know what the variance is. They're yoked together. So if I had a binary outcome, I don't have to worry about violations of normality if I don't use normal. I just swap out a different distribution for it. The other piece that these models add is something called a link function. What that does is essentially trick your model into creating predicted outcomes that stay within the boundaries. You transform what is being predicted into something that could go on forever, and then through the link function, it back translates into the data that stay bounded. It's a very complex idea, but the end result of that I want you to take with you is that these models ensure that your model can't predict impossible values. Like it can't predict a category of 6 if there's only 5. And it can't predict a count of -10 because it understands that counts stop at 0. So that's where the utility lies, is in dealing with boundaries, because boundaries cause non-normality and boundaries cause heterogeneity of variance or non-constant variance. So this class is actually, I created this class to follow intermediate, like directly. I did that on purpose. It's being offered in the spring. I don't know who's teaching it or what they're covering, but here's a link to the last version of the class, which will live on the YouTube as long as possible. So if you want to learn these techniques, you can make use of these materials on your own whenever you wish. So this class covers generalized models, but then it also adds 2 other things that are sort of adjacent. One is multivariate models, so you can do path analysis, which means like, does this predictor predict this outcome and does this thing predict this thing? Like those kinds of like stacked layered regression models are called path models. And it also covers, as a this little special topic, something called quantile regression, which essentially allows you to predict the median instead of the mean for your outcome. And the median is far more robust to outliers and non-normality. So if you're on the fence as to how to deal with your outliers, you can pick this strategy instead, and then you don't have to worry about them. And it's super easy relative to some of this other stuff. So I feel like this is one of those things that I wish I learned earlier. The other thing that we have to worry about is the residuals being independent. So there's a phrase that you will see in stats textbooks that the assumption of general linear models is IID. And what that means is residuals are independently and identically distributed. Identically means constant variance or homoscedasticity. Well, that seems okay, right? Should residuals be independent? Do you know what the opposite of independent is? I would say dependent. I've actually seen papers where they say non-independent, and I'm like, are you kidding me? Like, no, dependent. Dependent means correlated. So the issue is, are there people whose outcomes are more alike in your sample than other people? So as an example, let's say that I have a measure of something that happens pre an event, like a training program or an intervention, and then I measure what happens after. Do you think that the residuals from the same person being measured over time are going to be related? I do. They're going to be highly related. How well you did at pre-test is going to be related to how well you did at post-test in most cases. So that would be a clear violation of independent. More generally, dependent data or dependent residuals result from sampling over multiple dimensions simultaneously. So if you have occasions and you have persons, the occasions are going to be related to each other if they come from the same person. If you are measuring students And you're measuring students from multiple teachers or multiple classrooms. The students from the same teacher may be more related than students from different teachers. And if you have multiple schools within multiple districts, right, the schools from the same district might be more related than schools from different districts. So particularly within education and the College of Ed, dependent data is the norm. Like I can't think of any examples that don't have it. So longitudinal or repeated measures data, clustered data is what this is called, and also dyadic data, like if you measure two partners who work together, or a caregiver and a patient, or a kid and a parent, like those responses are going to be related because they're part of the same relationship. So those are all instances in which a general linear model would be insufficient. The consequences of ignoring this are pretty big. So if you ignore correlation in your residuals, basically everything's going to be some shade of wrong. The issue with sample size is that you don't actually have as many independent cases as you have people, because if people have some commonality to them, then it's like you have fewer people in terms of the information they provide. So that can lead to standard errors that are wildly incorrect. And then there's also the issue of what a variable means. So if I think about what things affect me doing better today than I did last time, that's like a different set of processes than what affects how I compare to some other person. So even if a variable is measured, like it's one variable, conceptually it's sort of two if you have 2 dimensions of sampling, and it could be 3 or even 4 if you have more than that. So you need a model that allows you to build in expected sources of correlation. So in this case, for simpler designs in which there's very few alternatives, so like each person is measured 2 times or 3 times and it's always at the same times, you can fit that as a multivariate model. Essentially, you would tell your software, I want to do a regression that's predicting pretest and post-test at the same time, but I want the pretest and the post-test from the same person to be correlated. You can tell the software to do that. And then you're not assuming that it's independent. You put the dependency in there as a correlation. For more complex designs, such as students who are nested in multiple classrooms, then you need a different approach. And this is where the world of multi-level models is my preferred terminology. It's also called mixed effects models. That's terminology that's used in design of experiments. And traditionally in education, people also use the term hierarchical linear model. All of those are synonyms for the same thing. And I have a link to a recent tutorial that I wrote with a former student to sort of get folks introduced into the idea of multi-level and where the research is on it and the current. And there are courses, again, these are the ones that hopefully will live on YouTube for as long as I can, to cover what these models look like for each of these different kinds of sampling designs. So I cover longitudinal and repeated measures in this class, and then clustered or nested data or cross data too in this class as well. And the reason that I didn't do that in this class is because to do it right requires a whole different method of estimation, and that introduces like a whole new set of language and procedures and things, and I didn't want to try to shove that in here. So just know that like traditional stuff for like dependent samples is sort of a special case of a broader world that allows you to have a lot more flexibility than what those models allow. And then last but not least, what about measurement error? We haven't talked about that at all. But do you think that the variables in your analysis are going to be perfectly reliable? Maybe. If it's something like height, like I can get my yardstick out and measure height. But if it's something like self-esteem or self-efficacy, you would ask somebody maybe like 8 questions, you'd add them together, and you'd say, this is their self-efficacy, right? Is that the same as like height or weight or something that's physically measurable without error? Nah. So normally what folks would do then is have to demonstrate that their scale is reliable. So they would report like a Cronbach's alpha or something like that to say, here's my reliability coefficient. It's good enough. I'm going to use it. But then in these models, we don't incorporate that information about how unreliable it is. We pretend that it's perfectly reliable. And there's a whole literature on this. Basically, measurement error can really cause problems because then your variables are not as related as they truly should be because the error is sort of like swamping things out and canceling it out. So these same kinds of general linear models can be estimated using latent variables, meaning the variable that is ostensibly purged from measurement error. So it's not something you can directly observe, it's something that you try to estimate. And measurement models are the way in which this occurs. So latent traits, latent factors, latent variables, latent constructs, all of those things go with this idea. And you can learn about how to do latent versions of these models for measurement purposes in a couple different classes. I think IRT is being offered next semester, but I would not recommend that as a follow-up to this course. There's too many steps in between that I think would be useful to have first. And then structural equation modeling was also just offered, and so here's the last version of that I teach. And I teach it from a generalized perspective where we talk about predicting scale item responses that are either numeric or categorical or what have you. So those are some other directions that where you can eject to if your model isn't supported. So that's a wrap. Non-constant variance, fix your standard errors somehow using some kind of empirical method. Not normal residuals, you might need to eject to a generalized model. Not independent samples, you need some kind of multi-level or mixed effects model. Not perfectly reliable, you need some latent variables. So these are all things you can stack on top of what you've learned in conjunction or in isolation as needed. So that's my story. And I conclude with thank you, and I hope this class sucked less than you feared. That was my end goal, suck less than expected. There, I promised 25 slides, that was it. So thoughts or questions, reactions? Clapping. Yeah, I think we all deserve a round of applause. We made it, folks. Yay for us, indeed. Well, I will tell you that you have forever earned the right to bother me. Okay, I'm changing universities, but I'm not dying, at least as far as I know. So if in the future you're looking for an example, like I need to do this, I don't know how, I'm happy to point you towards examples that I have in my collection of course materials that I've built over 20 years or so. I'm happy to try to give you resources or directions for things as much as needed, because I really do hope that you find these models useful in your research and that you can become a skilled method user, whether you're qualitative, quantitative, mixed methods, or what have you. So. The chats and the chat is blowing up over here. Thank you, everybody. Thank you all for your attention. Thanks for sticking with me. Office hours next week, Monday, Tuesday, Wednesday. Michael has his on what days again? You said...
Yeah, office hours on Friday and on Monday. And I will just toss out there, even though this, just for clarification, Lisa did not ask me to say this, but if you run into me or you have a question, I am on campus for the next probably 3 or 4 years, and you want maybe a little advice on one of these models, you can reach out.
That's very nice of you. So you've earned the right to bother him too, it sounds like. All right, well, I will let everybody go then. Don't forget to do your course evaluations. Don't forget to finish homework 5. Thank you for everything this semester, and please take care of yourselves. I hope you have a well-earned break over the next few weeks. So, bye for now.